Hi, I'm Robert Quimby, and I'm from San Diego State University, and I'm going to tell you about spectroscopy. So in this lecture, I'm going to start off by just describing the differences between imaging data, photometry, and spectroscopy. There's actually a lot of similarities between the two. They're very much the same thing, but there are some practical differences between the two. So I'm going to focus on those differences. I'm going to tell you a little bit about how we obtain spectra as astronomers. So I'm going to tell you how spectrographs work. I want to make sure you have a basic understanding of the operating principles behind spectroscopy. And then I'm going to talk about data and how we actually go through the steps of analyzing that data to remove the signal that we're interested in. A lot of the same steps that are involved in photometry, but the big thing to keep in mind is that when you have spectroscopy, instead of just having one bandpass, you have many, many bandpasses, hundreds, maybe thousands of bandpasses, maybe more, that you're dealing with all simultaneously. So while it's the same steps as doing photometry on some level, you just have to have some ways of handling it all in one go. All right, so we'll first start by talking a little bit about imaging data and what we get from that, so we can compare it to what we get from spectroscopy. If I give you an image of an astronomical source, you can look at that and you can say, hey, there's something there, and there's not something there. All right, so you have some spatial information about what's inside that area of the sky, and you can see the relative positions of the objects, and you can say, if you take images over time, if one of those objects changes position, it tells you something about that object. It tells you it's probably pretty nearby, because if it's very far away, you wouldn't expect that to happen. So there's some information contained just in the position information of targets. You can, of course, look at the image and say, hey, this thing is brighter than that thing. And again, there's some information that's being conveyed by that. Maybe one of those objects is closer, maybe one is farther away, but you're learning something about the relative differences between those targets. And you can look at it changes over time. Maybe one of those objects is getting brighter and fainter over time. That's telling you something about the physics of that object. You can also say something about the angular size. If you have an image, you may not know the physical size, but you can say, hey, that one spends an angle that's this big, and this one spends an angle that's that big, or maybe a target is at below the limit of your sensitivity. So you can say, well, that one is just a point source as far as I know. And that, again, tells you something about it. If you have just one object that's very far away, it's going to just look like a dot. But if you have a collection of those dots in, like, say, a galaxy, then you can say, hey, we got a lot going on there. Of course, one of the most important things you can do with photometry is you can assess the color of an object. That's just the relative brightness in one bandpass compared to the other. That's telling you something, again, about the physics of the object. If it's a bluer object or if it's a redder object, maybe that's telling you something about temperature, or maybe it's telling you something about dust. There's some information that's contained in the color. And obviously, the more color information you get, if you get different band passes, you can get a better picture of what's causing those color differences between one object and another. And that is actually what leads us into spectroscopy. We're just going from, instead of just having, we have one black and white image, to we have two images in different band passes, to we have many, 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 many different band passes, all with different flux densities. And we can use that information to learn something physical about the objects. So let's start here with an image. This is a real image that was taken by a Sloan Digital Sky Survey. And you can look at that image right away and you can say something about that object. This object that we see on the screen here is probably a galaxy. And I can say that because it's extended. The mission is not just at a point source. So even though it's very far away, we can see the light spread out in our imager. Whereas this source right here, that could be a star, could be a supernova related to this. But we can't resolve that object. There's maybe a little galaxy here. So there's a lot of information you can see just by looking at this. But you can't tell me much more than that. You can't tell me what this galaxy is made of. You can't tell me, is this galaxy moving towards us or away from us? To do that, that's where we need spectroscopy. So Sloan Digital Sky Survey actually took a spectrum of this galaxy as well. So they put a little aperture around this core of this galaxy, and they pass it through a spectrograph, the light they pass through a spectrograph, and they learn something about this object. So let's take a look at those data. let's start with just the spectra. Do it twice. And this is the spectra from the Sloan Digital Sky Survey. So you can see we have wavelength here in angstroms, and this is thousands of different band passes here, right? Thousands of different little bins that I'm plotting here. And this is flux density here. And you'll notice that, okay, first there's this continuum. So basically any wavelength you pick, you're getting some light, and it's pretty smoothly connected here. But on top of that, there's these emission lines that pop up. And these emission lines are telling us something about that object. It's telling us it has gas. We're learning something about the chemistry just by looking at the spectrum here. We can also tell that there's starlight in here, so there's gas in the galaxy and there's starlight. So all this information is contained in here. And if we look at these and we can identify, hey, I know these lines, they're oxygen because in the laboratory I can make a spectrum that looks a lot like that, except for it's shifted a little bit. Now we can actually figure out what the redshift of this galaxy is. We can say how fast is that galaxy moving away from us. So all that is contained in this spectrum. So let's compare now what we're getting from spectroscopy to what we were actually seeing before in photometry. So all we were doing with photometry is we were taking the same light that we're getting from that galaxy, and we're just using bigger bins to image it. So that image I showed before, I think, is with G band here. So we have a band that spans 1,500 angstroms, and any light that we get within that spectral bin, we're all integrating together. So we're integrating, we're kind of doing a convolution of this filter function here with this spectrum here. And from that convolution, we get one number, 15.6. Now, that's the number you get for all this right here. For all these thousands of little different spectral bands that we get in the spectrum, you only get one number. So you can see if we just had the photometry here, we can't directly say, oh, that object has oxygen in it. We might be able to guess, but we don't know for sure. And we might be able to guess at the redshift, looking at how the light falls off with color. But with spectroscopy, you can get a very precise measurement of it. So again, all the difference between spectra and imaging is really not so great. It's just that your band passes are smaller. So instead of having huge band passes that span thousands of angstroms, maybe they only span 1 angstrom or 10 angstroms. They're much, much smaller. So through the spectra, you can evaluate what the temperature of an object is. You can look at the composition, as I've been saying, the oxygen or hydrogen, silicon, sulfur, what's in it. And you can also do this line of sight velocity. So there's a lot of information that you can pretty directly get from spectra that it's very hard to get from broadband photometry. Of course, if you take your photometry, instead of doing those broad bands, if you did more narrow bands and you did more of them, then you get actually a better picture of what that galaxy was made of and what its temperature and maybe even redshift were. But what you're doing there, and really what you're doing with photometry, broadband photometry, is actually low resolution spectroscopy. You're just doing it in sort of inefficient way. If you wanted to know what the spectral energy distribution of an object is, you can take one image and take another image and take another image, each in a different narrow band, or you can get one spectrum where you get all that information in one go. So the key difference really between what we call photometry and what we call spectroscopy really just has to do with this quotient, this quantity here, resolution, spectral resolution, which is just the ratio of the light wavelength of the light that you're looking at to the spectral bandpass. So delta lambda here is telling you how wide your bin is in angstroms, and lambda is telling you what the center wavelength of that bin is. So for photometry, we have band passes that have a delta lambda of 1,000 or so, and they have a lambda of around 5,000. So you have a resolution of 5,000 divided by 1,000, so about 5. So broadband imaging, you get a resolution of 5. Whereas with photometry, with spectroscopy, typically you're working with resolutions of 1,000, or could be even higher. You can go up to 100,000. So there's an old adage that a picture is worth 1,000 words. So if you work out the math here, instead of doing a resolution of 5, if you're doing a resolution of 500, you get 100 times more information. So spectrum must be worth 10,000 words. It's just math, people. But there's a cost for those words. Spectra are difficult to get because when you take all the light that you're getting, and these are, if this is a faint object, it's far away, you're not getting so many photons here. And when you start spreading out that spectrum and just dividing it into smaller and smaller spectral bins, each one of those spectral bins is going to get fewer and fewer photons in it. So it becomes hard to get a significant detection in each one of those spectral bins. So what you really need when you start doing spectroscopy, if you want to do spectroscopy of faint objects, you really need a large aperture telescope. Okay, so hopefully we've motivated now why we want spectroscopy. You know, it's in one shot. You can say what the composition is, temperature, radial velocity is of a target. That's great. How do we go about doing that? So now let's talk a little bit about how we can make a spectrum. You probably already know this. You know that you can take in light, and that light travels at different speeds through different mediums, so depending on wavelengths. So if you're very clever about this, about how you organize your media, you know, going from air to going to glass to going to air again, you can make a prism, and that will take white light and disperse it into a spectrum. This is sometimes used in astronomy as professional astronomers. We sometimes deploy prisms, but actually we don't use these too often. A more common is something like this. This is a grating now. So in a grating, you have some material which has a pattern in it. Let's start with just a bunch of slits in it, a bunch of little notches cut through it so light can pass through those slits. So what happens is some of the light goes straight through and you get an image. But at angles, when you move away from there, you also get light that's going in that direction. And if you get light going through one of those slits and another of those slits, they come together, they can form a bright spot that's wavelength dependent on your detector. So instead of just getting one image, you actually get an image, and then you can get a spectrum, and you get another spectrum that mirrors that. So this is all symmetric, and you actually get these higher orders of spectra coming up as well. How does this all happen? Well, you guys have probably done this experiment before, where you take a laser and you have a double slit, you shine the light of the laser through, and depending on the path length difference, you're either going to get constructive or destructive interference on some target screen. So let's just work through the geometry on this before. You have some slits in some mask. These are separated by some distance. And what you care about is when these two paths reach your detector off at some distance, are the wavelengths going to be in phase? And you can figure that out by looking at the path length difference here. This is d sine theta here, or theta is this angle away from the direct line of sight here. And if this quantity is an integer multiple of the wavelength that you're using, so you got that laser at some wavelength, if it's an integer number, that means that the light's coming in from one slit and light's coming in from the other slit, and they're going to come together in phase at your detector. And so you get constructive interference. If it's a half integer, if it's not an integer, then you get destructive interference. You got a wave that's coming up, wave that's coming down, and so they won't, they'll destructively interfere, which of course means that that's not going to happen. You're not going to get those two photons going in that direction. They're either going to be absorbed or scattered, but they're not going to go to your detector. All right, so let's just do a little kind of toy demonstration of this process. You've done this before, but there's an important wavelength dependence that you may not have considered before. I want to make sure this is clear to you. So I've got a little fake detector here. We're just pretending there's a screen, and there's two path lengths from two different slits in there. And we're going to look at whether we're getting constructive or constructive interference, depending on what the wavelength is that we're supplying. Oops. All right. So first, let's consider some wavelength of light, so 0.11 in whatever units. Maybe this is some red laser that you're shining through the slit. And when we do that, this is what you're getting. So this is just intensity plot here. So, you know, intensity of 1, you got constructive interference. Intensity of 0, you got destructive interference. So on your detector, there's some center line here at 0, and the two waves they are in phase, and they come together and they make a bright spot there. And then when you move away from that, you get destructive interference, and then you get constructive and destructive, constructive, destructive. So you get these bright spots as you move away, but they're discrete points. You get a point here, and you get a point here, and you get a point here. All right. So you've all done this, hopefully, with a laser at some point. What you may not have done is use two lasers. And it's kind of a shame that we don't do this experiments with two lasers. It's maybe a little more than young students can handle when we first encounter this. But let's say we had a blue laser, not just a red laser and a blue laser, but we had not just a red laser, but two lasers, a red and a blue. So we have a shorter wavelength here, and we're going to go through the same process, and we're going to keep in mind that there's a wavelength dependence here on where we get those fringes. So at different angles, if we have a different wavelength, the interference is going to be constructive or deconstructive at different angles. So that means when we go here and we add our second laser to this mix, this is what we get. So again, at that 0th order, they both come in phase and we get constructive interference and we get a bright spot. But as we move away, we get these little bright spots moving away at different orders, but at different places for different wavelengths. The red, that's our longer wavelength, you have to have a greater angle away from the center line to make a bright spot at each order. The blue ones needs a smaller angle. So what we start getting here is dispersion. The light is dispersing as a function of wavelength. And this is the key behind spectrographs. So this is a nice little image here looking through a grating. So we have in front of the camera, there is a grating, which has a lot of these little tiny slits in it. There's so many and they're so close together that you can't see it here, but they're all there. The advantage of having lots of slits is that you get a lot more light that you can pass through, but they all still have to go through slits, and that means you still get this interference effect. So behind the grating, there's a little light bulb here, some incandescent bulb, and because of the grating in front of the camera, the light is dispersed. So we get the 0th order image here, we get the +1 order here, and the -1 order here, and then of course there's higher orders if we could see them, 2nd order, 3rd order. And always note that the blue light is at the smallest angle from the 0th order, and the red light, the longer wavelength, is at a greater. And this is symmetric. So that's a transmission grating. We don't have to do it this way. Actually, any repeated pattern, whether the light is shining through it or reflecting off of it, will cause the same effect. So the geometry is basically the same. You have rays that are coming in. They're bouncing off of different structures. If you have this repeated grid here, what you'll get is reflected rays, and there'll be a path length difference. And again, same thing, d sine theta for that path length difference. So depending on what the angle is away, you're going to get constructive or deconstructive interference as a function of wavelength. I should note that you, right now, I'm convinced that you have access to a reflection grating just like this. Most people don't have transmission gratings lying around, but almost everybody these days, especially you, the viewer, I know you have a reflection grating at hand. It's the monitor in front of you. Whatever you're looking at, if you have a screen, if you're looking at this on your phone or if you're looking on a computer, that screen has a set of pixels, which is a regular grid, right? And so if you look at reflected light off of that, usually you're looking at emitted light, but if you're looking at reflected light off of that structure, you'll actually see spectra. So you can do this. The easiest way is if you have a phone, turn on your light. You need a point source of light, a very small. So the lights on phones are actually pretty good. And then what you look at is you look at your screen, hold the phone like this, and look at the reflection of that light in your screen. And what you'll see, don't look at my phone. You got to look at your phone. Get your own phone. And look at the screen, and you'll see little rainbows coming around the 0th order image of the light there. All right. Okay. So that's the setup now. Now we know how we can make spectra. All we have to do is we have to disperse that light and then just take a picture of it. And we can analyze that just like we analyze imaging data. So let's start off now with how we actually set up our instruments to take this data. So we'll start with just a basic image. So we have a telescope. We got light coming through. We focus it. We can take an image. Maybe this whole thing is our detector here, and we got these different stars that we can image. This may be right ascension, this may be declination. This is what we've done before. Now what we want to do is we want to disperse that light. So somewhere in the path, we're going to put in our dispersive element. And this is what we get now. So this dispersive element could be a grism, or it could be a prism, could be a grating. I'm going to assume it's some kind of a grating. So that means you're going to get your 0th order image. So we're still going to see stars. and you're going to get some a spectrum from that. And actually, you probably get multiple spectrum. You get higher orders, you get negative orders. Just to make it a little simpler, I'm only showing one order here, the 0th order and one dispersed order. So we can see what happened here. We have our dispersion axis set horizontally here. So the light is dispersing horizontally on the image. And what ends up happening now is that some of these objects were kind of horizontally oriented to start with. So light from this spectrum is now overlapping with the star that we had there. And this is going to make it hard. If we take a picture of this whole thing here, how do we know the light coming here? Is that from this star here? Is it from this star here? Makes it a problem. So what we do next is we put in a mask. When you add a mask, you can block out all those other sources, and you just have one source now, or whatever is in this one line here. If I had another source here, I'd get another spectrum. But you have a source in some allowed region, and you have masks that's blocking everything else. And so you get the light from that object coming through, and it makes a spectrum because you have your dispersive element in. A little bit of trickiness on the terminology here. So this mask that I'm using is very long and it's narrow, so we call it a slit, but this has nothing to do with the double slit experiment we were talking about earlier. This is not causing dispersion. Remember, before we put that mask in, we already had dispersion, right? It was already there. All we're doing when we adding this mask is we're just blocking out light. It's just we call it a slit, but it's a slit mask. All right. So this allows us now, we can image this part of the spectrum here, and we can record that data on our CCD, and we can then analyze it and figure out how bright is it at each one of these different wavelengths. One tricky thing that you should keep in mind is that your detector is going to be some finite size. So maybe this little rectangle here is the size of your detector, your CCD, right? It could be smaller than that spectral trace that you have, right? So in general, you're only going to get some fraction of the electromagnetic spectrum on your detector. And you may have some options with your instrument to actually place this detector, or more commonly, you can actually tilt the grating so you can make that spectrum move to wherever your CCD is, so you can image the part of the spectrum that you're most interested in. So let me show you a layout now. This is a real layout for the Keck LRES spectrograph. This is on the Keck 10-meter telescope, Keck 1. So this little schematic here is just kind of giving you a cartoon view of how the instrument works. Light comes in through the telescope. It passes through that slit mask, right? Just the mask. It goes through a collimator. And let's ignore this blue channel here. Some fancy spectrographs have 2 channels, so you can have a detector that's imaging the red part and a detector imaging the blue part at one time. So if we just look at the light that comes through here, we can put a mirror here, and then light will just go through and we'll get an image. Or we can change this mirror out and put it in a grating, and then instead of getting just a simple image, we'll get those spectra will start landing on our detector, which is down here. And we can change the angle of this, so we can move those spectra across our detector and get the part of the spectrum that we want. So after we've done this, we've imaged it. What do we see on our detector? Well, we see something that looks roughly like this. This is a cartoon. This is not reality, but this is demonstrating what you're going to see. So we have our CCD area here, and on that, we have a light from a target. That light is dispersed across this way. So it's important to understand that we have a wavelength coordinate. So as we move from left to right here, we're changing the wavelength that we're looking at. Each one of these is a different wavelength bin moving left to right. As we move from top to bottom, we're changing the spatial coordinate. So we have an object which is located around pixel 100. So we have that long slit in some spot in there. We're getting light from a source, and there's no source at any other positions there, right? So if we had another object over at position 40, we'd get another trace across the field like that. But for this example, we only have one object in our slit, our mask. Now you may be noticing there's some lines that extend across the CCD at certain wavelengths. At this wavelength, for example, at wavelength 100, whatever units those are, we get light at any position we look at. All right? Keep that in mind. This is spatial position. So at any position you look at certain wavelengths, you're getting the same amount of light. So what this is telling you, this is our background. So this could be light from just the air around us. The spectrograph is picking that up, the air in the atmosphere. So no matter where you look, you still are looking through air, so you're going to get some amount of light shining through. And that air above you does have some continuum, but most importantly, it has some emission lines. Right? So the night sky, it's a gas, it's excited, it's at some temperature, so it is going through transitions and producing emission lines, just like gas in a laboratory. So these are very important. They can they cause a background, a wavelength-dependent background for your source, but they have some advantages. We can actually use these for wavelength calibration. I'll just note that if you had real data, so I'm doing this in a cartoon version, so the lines are going straight across like this, and the wavelengths are straight up and down. Real data, the trace is going to be kind of tilted on your detector, and these wavelength lines are going to have some curvature in it. So figuring out where each one of those wavelength bins is as a function of position on your detector is one of the tricky parts, one of the most tricky parts actually of reducing a spectrum. So what we want now is we want the light from this traced object here as a function of wavelength. We want to know what the flux density is at each one of these wavelength bins here. We got 512 in this example. So each one of those, how bright is it? And this is called extracting the spectrum. So we take that two-dimensional data and we're going to get a one-dimensional answer, which is just the flux density as a function of wavelength. So I've kind of said this before, just remember, all we're doing here is we're doing photometry, but we're just doing it many times at once. All right, so for each one of those wavelength bins, we have light from our source and we have background light, all right? And what we need to do is we need to figure out how much light are we getting from our source and how much is contributed by the background, remove that background component, and then we'll have how much is coming from our source. And we do that for each one of our wavelength bins. We got ourselves a 1D spectrum. So first thing let's do is let's extract the spectrum. Let's take the whole image, and just for each one of those columns, we can say, well, this is one wavelength, so let's just integrate along that entire column, and we'll get the total amount of flux on the image. So to do this here, we just take the image that we've generated, and we're just going to sum it along columns, which is axis 0. There we go. So this is the whole image now, the whole 2D image that we have just integrated, we've marginalized, if you want, over one axis, the wavelength coordinates. We have those 512 measurements that we've got now. And at each one of these wavelengths, we have some amount of total light on the image. So you can see there is this kind of curve here. That's our trace that we want. But on top of that, there's all these emission lines from the sky. And of course, we have to deal with this. So one thing we can do right off the bat is we can narrow that aperture for extracting our source. We can just kind of put it where we know the light comes from our source, because it's not everywhere. So what we just did is we integrated all the way from top to bottom on this image for each wavelength, but our source is only here. So maybe if we just extract this region here, maybe from pixel 80 to 120, then we can get just light, will be more dominated by light from our source. So we'll just do columns 80 to 120. We'll do the same process. And there we go. So we still have light from the background, but now we're a little bit more weighted towards the target light that we care about. So then the next thing we need to do is, of course, we need to subtract off the contribution of the sky as a function of wavelength. So what we do for this is we have our sky measurements, which could just be we can just use the image. So we'll take the image data we have, and then in a different part, where we don't have that trace, we'll just say, okay, how bright is the object here? So we need, so we have 40 columns here, so we're going to go from maybe column 20 to 60, where we have no light. Sorry, row 20 to 60. And then we just take the image where we have the target and the image where we have the background, subtract off the background, and we'll have just light from our target. So this is very analogous to what you do for photometry. You always have to subtract the background light, but now we're just doing this 512 times at once. So now we have some wavelength coordinate here, but we don't know what those wavelengths are. So we need to calibrate this as well. And the way we can calibrate our wavelengths is by using known emission lines. So a popular way to do this is to take a lamp where someone has taken the time in a laboratory to calibrate what each one of the wavelengths are that are emitted by the lamp. We can just use skylines, maybe in this case. So if we use just our sky background, and we'll just sum that over columns, we get this. So now if I know that this line here, maybe this is an oxygen line, it has a wavelength of 5577. I know this line, I'm sure it's this. I can identify these other lines. These are OH lines or some other lines. Now I can do a mapping between the known wavelength of this line and the coordinate here, and I can create a wavelength solution. So then if you give me any wavelength coordinate, I can say, well, this is the corresponding wavelength in angstroms. You also may want to calibrate the flux densities. So each one of those wavelength bins, you're getting counts at this point. So we know that we have 10 counts in this bin. But what is that in flux density? So the way we do this is the same way we do it for photometry. You observe a star that has a brightness that's already been calibrated. So we know in that wavelength bin, the brightness of this standard star, it's been calibrated. And so we say, okay, well, we got 100 counts in this bin and it has a flux density of this. So then we can calculate effectively a 0 point for that wavelength bin. And we can do this for every wavelength bin. Each wavelength bin is going to have a different 0 point in using kind of a photometry speak here. And so we can calculate as a function of wavelength what our 0 point is. And that'll give us a way to take that whole spectrum we get and turn it into from counts to flux, the flux density. All right, so I give you kind of the cartoon version here. I want to show you some real data now. This is a real spectrum of an arc lamp. So we have, column number here, row number here, dispersion is happening along this way. So all these lines here, these are lines of constant wavelength from a lamp that was illuminating the slit. And we know these wavelengths. People have calibrated these in a laboratory, so we can convert now from pixel coordinate and column number into wavelength number. Next thing we can do is we might want to flat field our data. So you remember at in each wavelength bin, right, we have a whole set of pixels. And there might be differences in the quantum efficiency of the detector from pixel to pixel. So we might want to correct for those. Now to do this, when you're doing imaging, you may be used to taking one image where you assume all at the top of the aperture, you get the same number of photons incident, and they go through the whole optics. And on the detector, you can just say, well, this pixel got 10,000 counts and this one got 9,000 counts. That means, well, the ratio of this is telling me something about the relative efficiencies of these two. It's a little more complicated with spectroscopy. I can't just do that for this whole image here because the brightness as a function of column here has something to do with the spectrum that we're illuminating the detector with. So we may have some lamp that might have more red photons than blue photons, or more blue photons than red photons. You don't know the temperature. We don't have the calibration for those things in exact terms. So what we do is we say, okay, we know now from our wavelength calibration that here's a line of constant wavelength. And so along this line, we're going to say, what is the typical number of counts? Maybe it's 5,000. So say, okay, for each one of these pixels in that wavelength bin, we're going to divide those by 5,000, and then we'll get the relative sensitivity from pixel to pixel. So we can use that to calibrate our images to correct for flat field variations. Then we can take a standard star observation. So we'll go to, again, a star. We know the flux density at each one of these wavelength bins. We measure how many counts we get, and then we can get our conversion factor. We get a function to convert from counts to wavelength, counts to flux density as a function of wavelength. And then finally, we can move on to our science spectrum. So this is a real science spectrum taken by Keck. This is the object that we're caring about here. And then when we do the hands-on session, this is the object, this is the data you're going to be working with. So this trace here is actually of a galaxy. You can see it's got little emission lines here. And so if we can extract this spectrum and we can figure out the wavelengths of these emission lines, and we can identify them, we can say, hey, that's hydrogen there, that's oxygen there. Then we can figure out what the redshift of this object is. And that's going to be what you're going to do in your hands-on session. So I look forward to seeing you in the hands-on session. Good luck getting through this, and let's have some fun.